Hi and welcome to a discussion with Daiqing Li regarding DreamTeacher Pretraining Image Backbones with Deep Generative Models. As the name implies, we're going to focus on image backbones in this session and primarily how we can train those. And the contribution of this particular paper is to use generative models for that purpose. So I hope you like it. So we will be talking about how to train image backbones. I guess is the kind of core idea behind this paper.
Yeah.
A good starting point would be to talk a little bit about image backbones. I haven't had a video on it yet, so it would
Mm.
be good if you could give an intro to that topic and we can expand from there.
Yeah, sure. I think it's just like it's a good starting point for some background knowledge. It's like, um, I mean, in vision field, um, there's like a transition from like convolution neural net based model, if you are familiar with. It's really start from like, for example, just like conv layer stacking, like for example, VGGNet or ResNet. I think most of people heard of.
Hmm.
It's been used for a lot of tasks because it's efficient. Um, and then usually people, um, very important like pre-training paradigms is like when you initialize this backbone, right, those are just like some random weights, right? Some matrix. You can think about it just like randomly initialized. Um, and if you want to use that for some, for example, like some perceptual task, let's say you want to segment out someone's face, for example, like you want to do some driving scenario, um, instant segmentation, you want to do some classification on ImageNet. Usually you need to have a lot of like labels, right? So and what people found, like I think in history, is like they need to find a way to pre-train those backbones. So basically, you need to define some pre-training objective, and then you fine-tune on some like small set of labeled data set. For example, like segmentation or some tasks I just mentioned. One like I think a common task, right? It's ImageNet pre-training. I think in this field, like back to 2020, sorry, 2012, right? Like ImageNet challenge is because like you have such a large scale ImageNet at that moment. It has around like 1 million image with
Hmm.
the 1,000 classes. And then just pre-train on that, right? You pre-train on that like a classification task, and then you fine tune. That's the common paradise, right? But recently there's also uh, like people try to go beyond that, right? They try to find some like pre-training tasks without any, like image labels. One thing is like, it's very hard to find such labels. Face
Hmm.
Lab, they spend like, I don't know how, if I recall correctly, I think it's like $50 million just to
Hmm.
label this ImageNet. Uh, and one thing is like they can do what they call self-supervised learning, right? It's like, okay, so if you don't have any labels, like what can you do, right? So
Hmm.
one paradise is basically, okay, can we, like just do some masking? For example, like imagine you have a lot of unlabeled images, right? Like you just randomly mask out some patches, and then you try to predict. So given some unmasked patches, you're trying to, predict the patches, right? That's one paradise. And then, there are other paradise. For example, like you can doing like a clip base. Basically, you have some noisy language description for that image, and then you try to maximize the similarity, right? Let's say you have a pair of the image and description, right? You try to maximize the similarity between this pair.
Hmm.
While minimize the dissimilarity with some negative pairs, right? That's
Hmm.
called contrastive pre-training. It's also one paradise, right? But I think what is less underexplored, which is also the main, I think the paradigms we're trying to propose in this paper is the what they call, like basically, can we use some like deep generative models as a teacher, right? I think back at the time, this paper it was like already ICCV 2023, right? It's a little bit old, but I think the idea is still like very interesting because you see nowadays there's a lot of like foundation model, right? For example, like stable diffusion or like there's many like flux, right? Recently, they train on this large scale data set, right? Like they have very good representation for the backbone, sorry, for their generative models. And I think in this paper we're just trying to propose like a general framework, trying to distill the knowledge learned from those generative models.
Mm-hmm.
Yeah, so it's a lot
Maybe
of
to take maybe to take a few steps back here and follow up with some questions. So
yeah.
if we're coming back to image backbones in general, I take it that those are networks in themselves with the task of extracting features from an image input. So you feed the backbone an image, and out of that comes a certain amount of features.
Yeah, that's right. That's right. Uh, that's the general definition of the image backbones. Yes,
Mm-hmm.
and
Do you
people have.
normally tailor those? Do you normally
Mm.
tailor those very significantly to the application of interest, or are they more general in the sense that you have state-of-the-art image backbones that are applicable across domains, and you use a few golden tools, similar to how people use ChatGPT, for example, for just generative question answering? Or is
Yeah,
it more
yeah.
that the domain is
So
scattered depending on application?
yeah, um, I think both. So at the very old days, right, when it just happens, like people trying to just tailor it, as you say, like for specific applications, right? Usually it's like for academia, it's a super small scale. Usually
Mm-hmm.
they get some like very good performance, but later, I think right now or just like after convolution neural or ResNet, right? Like everyone trying to just standardize this, right? They try to have like a very large backbone, image backbone, but it's general purpose. But still, there are a lot of engineering happening during this like past, I don't know how like 10 years, right? People just like trying to, engineering the backbone, and then they test a bunch of those like application, right? Showing it's effective. Yeah, so
Mm-hmm.
that's backbone.
Mm-hmm. And if we come back to the training procedures for these backbones,
Mm.
um, you mentioned a couple of training approaches, for example, trying to recreate patches of an image that are masked or removed.
Yeah.
That to me seems like similar to how you would train a language model to
Mm.
learn the conceptuals of language. You're training a model to learn the conceptuals of images and how to generate those. How do you go from something like that to an actual backbone? Because
Mm.
you want in the backbone to extract features, and sure, the knowledge of the features is somehow encoded in a model that's learned the conceptuals of images in a good way. But how do you take the step from that training procedure to actually
Mm.
being able to generate a backbone or to have a backbone to generate features?
Yeah, that's a good question. So a lot of like vision backbones or recent like pre-training techniques in vision is actually inspired by the MLP community, right? Like you said, um, for example, like ChatGPT, right? GPT is like next token prediction. But before that, there's still like a very popular technique called BERT. So basically, you just randomly mask out some patches in the language sequence tokens, right? And then you trying to
Mm-hmm.
predict the missing tokens. So basically, what I said, like a masking technique, is very similar to that BERT paradigm, right? They're just trying to, mimic this process in the vision domains, right? And there's a
Mm-hmm.
paper called mass autoencoder. So basically, just like it's just similar to GPT, right? But it's just like the sequence becomes the vision tokens, and you randomly mask out some patches, right? And then you're trying to predict the missing patches. And people try hard to make it work, and I think still, right, even now, like people, there are a lot of like variation. Basically, how do you decide the training objective? How do you, what's the ratio of the masking? Yeah. And then after you pre-train that, back to your question, right? So basically, the goal was not trying to, uh, it's not a generative model, right? It's not like GPT is, it can, after pre-training, it can generate things. I think for masking, they learn more about, for example, some discriminative uh, features, and then they fine-tune their downstream tasks. But after the pre-training, it usually learns how to do reconstruction in a blurry way, but it's not like a GPT style, like you can do generative prediction on that. Yeah.
Clear. My question, more specifically, I think, is would you follow us? So if we go back to BERT, you would have a pre-training stage, and there
Yeah.
the model would get the conceptual understanding for syntactical features of a language, and then, or also higher level features, not just specific to one language necessarily, but higher level features. And then you would have a fine-tuning stage where you would train BERT for the particular application that you're interested in. Is it the same if we're talking about image backbones, that you have a pre-training first, where you make sure the model gets the foundational understanding of images, and then you have a fine-tuning stage where you turn this large network into a feature extractor? Am I thinking about that correctly, or does it work in another way?
Yeah, it's a similar paradigm. Like you pre-train, regardless how you pre-train it, right? You can pre-train like in BERT, right? You predict the mask features, or you can pre-train it like traditionally, like ImageNet, right? You can pre-train it using like classification with a label. And then after this pre-training, you also do some fine-tuning. It's like the post-training stage, right? Like in ChatGPT, or you familiar, or people familiar with, like they use higher quality labeled data set, right? You want to do the post-training stage for the downstream task. Yeah, it's the same in computer vision.
Okay, so let's maybe then hone in a bit more on the generative network and the structure that you're looking to create image backbone. So you said before that you're using generative models for doing this. Could you elaborate then a little bit more on the approaches you're taking to
Yeah.
start with a generative model and then create an image backbone from that?
Yeah. So I think maybe before that, I want to mention another paradise. Maybe it's more related. So I mentioned there's like contrastive, there's some masking, and people also try to do next token prediction. For example, in like early day in OpenAI, they do like iGPT. They call like image GPT. So basically, it's just like they don't need any like modeling. They just like unpatch the, let's say you have an image, right? Like you have pixels, and then they just treat each pixel as like one token. They're trying to predict the next token as like a general purpose pre-training, right? So, but that you can imagine it's like super costly, right? For example, like image with like 1K by 1K, it's like super long sequence, right? Comparing to language, which usually is like under, 10K tokens length, right? You for one image you have like super long sequence.
Yep.
So for that training, I think it's a good try, but I don't think it's successful, right? So people have like more efficient pre-training, like I said, like masking, or and the performance is not super impressive at that moment. So back to the question. So how this related to this paper? it's like one intuition I think we had was, people in the computer vision, they spend a lot of years to do these tricks and engineering for this general purpose image backbones. For example, like for ResNav, for ConvNext, or for VIT. Even VIT, they have a lot of trick to make it works, right? So I think the motivation here is like we don't want to reinvent the wheel. We don't want to spend this effort. Like let's say they demonstrate it's a good way to a good structure for the backbone to do image tasks. We just follow, right? We also use that. What we propose is a way to basically to use some pre-trained generative models to distill the knowledge into the this already well designed and well engineered image backbone. Yeah. So in a high level, how do we do that? It's by feature distillation.
Maybe actually, if you want to answer that question, I can scroll down to figure number, whatever
Sure.
it is. I think there's a good overview. All right, so let's have a look at this then.
Yeah. So yeah, I list this as like if you look at figure A, is a reference for contrastive learning. So it's like you have a image backbone. Let's say it's a queue, and then you have language, right? So I think that's one, like you have two branches, right? It can be you contrast based on different modality, let's say image and language, or like in self-supervised learning, people trying to contrast on like two augmented. So let's say you have like the same image, but you just augmented uh, uh, in different view, right? For example, you just flip it, you just like randomly transform it, and then you try to maximize the similarity, right? So that's one paradise. So in our network, so you can think about the first branch, like on the left. Let's say it's a figure B, right? So left branch is like, just the same as like an image backbone, right? The only difference here is like for the right hand side here, instead of you journey train it with some other encoder, you train it using some like pre-trained generator, right? Let's say it's a GAN framework, right? You have some random noise, you can just randomly sample it, or it can be a diffusion model, right? You have some image, you encode it, right? You can denoise it to get some features, right? So in figure B here, how we do the training is like you have the backbone, and then you have some what we call like regressor. So basically, for different layer of features, because this generator usually when they design, they will have like different dimensionality, right? It's not exactly the same as what you pre-train. Like you can train on different like different size of the backbone. So the regressor is basically trying to map different dimensionality to the same as the generator. And then the law.
Can you reiterate on that point a little bit? So we say that we
Yeah.
have different dimensionality in terms of what? In terms of features, or in terms of like what dimensionality are we talking about now?
Yeah. So the dimensionality of the layers, right? So let's say it has some layer, for example, for uh, different vision backbone. But for example, like in each layer, you have some dimension, right? It might not match what is pre-trained on the generator, right? Let's say the generator is a stable diffusion, right? They chose their own dimensionality and model size, but it's not necessarily the same as, for example, the image backbone you're trying to pre-train, right? So in order to match, so the goal, you're trying to match their representation, right? So in order to match the representation, you use this regressor to map from the image backbones feature dimension to the generator's feature dimension. Does it make sense?
That makes sense. Are you
Yeah.
using intermediate? So what exactly are we getting from the generator? Are you using some intermediate layer? Because I'm assuming that's a network of some form as well, and that you're
Yeah.
somehow taking the output of an intermediate layer, and that the dimensionality of that intermediate layer then is what needs to be compatible with the intermediate layer of the image backbone.
Yeah, that's right. So in this way, I think it's just like a high, in this figure, there's a high level overview. So it abstract away the actual layers. But
Hmm.
if you go to next figure, figure 3, yeah, it's more clear here. For example, like, for the generator model, let's say you have like encoder and decoder, right?
Hmm.
So let's say it's like a diffusion model. So diffusion model, you have if it's a UNet, you have like some downsample layer, you have some upsample layer. So you can say the generator is like the upsample layers. So you can select some intermediate latent features, right? And then the output for the generator will be some feature vectors.
Hmm.
For example, let's say it's like G3, 4, 5, right?
Hmm.
2, 3, 4,
Yeah.
5, and then the same image goes into the image backbone, right? So the image backbone will also, it's just a network, right? You have some intermediate features, and then you're trying to use the what we call the feature regressor. So basically, some layers trying to map it to some sand dimension as like G2, 3, 4, 5, right?
Hmm.
And you have this feature regression loss. So I think it can be like MSE loss, or it can be some other type of like basically some similarity function saying these two features are similar.
Hmm.
Yeah.
Okay.
So that's that's a framework in general, I think.
Uh-huh. So I think this is a good figure to talk about the objective again of what we're trying to do. So we have the image backbone, and then we have the generative model here, and we
Yeah.
are able to extract a set of latent features from the generative model, and we're
Mm,
able to extract a set of latent features from the image backbone that we
yeah.
then convert to the same dimensionality. That's fine. And then we have some loss function here. With
Right.
this loss function, what exactly are we trying to do? Are we trying to make these features as similar as possible across the board? Or is there some more specific selection that we're trying to do here? What exactly is this loss tailored to do with the system?
Yeah, so I think we ablaze some losses on the feature regression. And one simple loss is basically MSE loss, right? It's inspired by the um, earlier work called like feature distillation. So uh, uh, in the literature, like knowledge distillation, like people try different way to, they have like student teacher model, right? So how do you distill the knowledge from a teacher model, which is usually very big and large, and they want to deploy this like student model, right, in practice. Usually it's like much smaller. So
Hmm.
one I think techniques like people use is basically they trying to map or the make sure the student features are similar to the intermediate feature of the teachers, right? So one
Hmm.
way is just like, okay, we do MSE loss, and then oops, sorry, and then there are other way to I think there are other losses. Uh, for example, like you can map if you go to equation 1 and 2,
Okay, so here's MSE and AT.
Yeah, there's like attention transfer loss, basically just trying to uh, emphasize what is important for the features, right? It's not super important. I think it's just like something we find works well empirically. But
Mm-hmm.
yeah, I think what's important is like basically we just define some similarity functions, and then depends on your pre-training objective. Like you can try like different setup. For here,
Mm-hmm.
it's just like some empirical results like we find works well. But in general, I think MSE loss simply just regress on the features should work. Yeah.
Mm-hmm. Okay, let's think again about where in the training procedure we will actually do this. So if we talk about this image backbone now, when we start the training procedure, is this image backbone pre-trained at all, or is the ambition to take really a newly initialized image backbone, just a
Mm.
random network, and pre-train it, if you will, or if there's another term, with this already existing generator model to then align the features as a starting point?
Yeah, it's a good question. So, um, I think we try, let's see, because we usually in this line of work, people trying to compare in ImageNet, right? So they will say, okay, we have like supervised pre-trained ImageNet. If you go to table 1,
Mhm.
yeah, here. So you can see like basically, for example, if you compare like convolutional backbone, like the first line is like supervised. So
Mhm.
you have like ImageNet data set, right? So in in order to compare the performance in a fair way, so usually people will just use the same pre-training data set. Let's say it's like ImageNet, right? Supervised means they use the labels, so as like one of the baseline, and
Mhm.
then there's like other methods. They also use the same data set, but they are self-supervised and they don't use any labels. Um, and you can see like basically for the comparison, like to other model. For example, you have Moco, you have Dino, MAE. Those
Mhm.
are all self-supervised, right? They don't use any labels,
Mhm.
but they use the same image. So for the pre-training, also for the same as our methods, because we have two networks, right? One is the generative model, the other is the image backbone, right?
Mhm.
So we also need to make sure that the generative model is like a fair comparison, that it doesn't use any labels, right? So we use a pre-trained generative model. It's called ADN. So this model is released also by OpenAI. So it's basically
Mhm.
like guided diffusion models, and then we don't use we just use that to uh, like a freeze network, and then we use their features as like a teacher signal uh, uh, to pre-train the sand backbone. So the pre-training procedure is like if you go back to the uh, figure, yeah, figure 3 here is like, okay, so the um, pre-training start by you feeding uh, the image from the image net, right? You feed the image net,
Mhm.
and then you use the pre-trained model to extract the features, uh, and then you distune the losses, right? Using the feature regression loss as a pre-training signal.
Mhm.
Yeah,
And then this image backbone that you're trying to train, that is trained from scratch then, if I understand you correctly, when you start this process.
yeah, that's right. You train from scratch. Yes.
Okay. Okay. What about the features that we have here? Do we have any control over those? Like what features we're able to extract, which not?
Mm.
And yeah, maybe if we start there, I have some more follow-up questions. But is there any way to control the features that we get, or at least visualize them and see what kind of features we're extracting? Something like that.
Yeah, that's right. So um, if you go to figure 4,
Hmm.
so I think one motivation we had was like, so if you just like um, we we're trying to see whether the genetic model has good features, right? So what we did is like you take this like diffusion model, you let's say you have this real image, right? You add some noise, right? Let's say like T here means the time steps, right? So like in diffusion model, you have like you condition on the time steps. The network is trying to denoise the noisy image into the clean image, right? So what we are
Hmm.
visualizing here is like, let's say we choose some time step, we we add noise for the to the clean image, and then we do a one forward pass of the diffusion model, right? And then we select some layers. Here, I think it's like uh, different scale, right, based on the resolution. And then you do some k-means clustering. Um, sorry, I think it's just like feature activation map, not k-means.
There
And
is
you
another
see,
one on k-means if you want to see it. We can scroll down to it. But
oh yes, but let me finish this one. I think it's just like basically you can see at different level of at different scale of the activation, it already developed like unsupervisedly the concept of like parts, right? Like you see some activation map focus on objects, and some layer it focus on the wheel of the truck. So it's very excited that because those features are unsupervised, right? Or it doesn't use, it's just like trying to generate it, but somehow for this intermediate layer, they aggregate those features for different, concepts.
mhm.
Yeah, we can see more clearly maybe in the k-means features. I think it's in figure 5 here. Yeah.
Yes.
Yeah, so it's more it's same story but with different network, right? So we uh, this one is GAN framework. So we're trying to show it like it works in general, not just for one particular pre-training. For example, for
Mhm.
diffusion model, it also works for GAN. So so what we are showing here is like for GAN's framework, if you extract some intermediate features and then you do k-means clustering, it already developed this concept like sky, car, traffic sign, um, those blob, right? So that means it
Mhm.
has some semantic understanding in those features, which are important, for vision downstream tasks. If you want to do depth prediction, you want to do semantic segmentation, it's all um, it's very critical to use those uh, features. Yeah.
Mhm. Okay. Good. There are two kinds of data sets that you generate. There's a synthesized one, and I believe the other one is called the encoded one. Um, could you elaborate a little bit on the two different approaches that you took there and why they're interesting for the study?
Hmm. Um, yeah, let's see. Uh, yeah, it's been a while. Sorry.
That's
Let me
fine.
try to recap. Like, do you mean uh, so which
So
data set?
as you're creating the feature data set, D,
Mm,
you're taking either a synthesized approach
mm,
where you're sampling from the prior of the generative model, as I understand
mm,
it, and with the encoded dataset creation, I'm not exactly sure. What you do there, you get some latent variable from the generative model, and then you somehow use that, I think, to um,
Oh, I see. Okay.
I'm unsure exactly how you use it.
Mm.
Yeah, but you use it indirectly to train, I think, the backbone.
Yeah, yeah. Okay. I see what it is. I'm trying to recall what it was. Yeah, so basically, let's say it's image from ImageNet, right? So
Hmm.
one way to pre-train it is just like you just use the image exactly the same as the real image, right? So your your feature pair will be real image plus the feature from the generative model. That's the real, what we call the real feature pairs data set, right?
Hmm.
But since it's a generative model, you can randomly synthesize some new samples, right? If it's for example, it's a GAN framework, it's a GAN network, you can just randomly sample some noise, and then you can generate some new sample of the image. But your image is like synthetic, right? And then you
Hmm.
can also we call this like synthetic uh, feature pairs, because you can in theory like sample infinite like this pair. Imagine like you don't need to find any new image data. You don't need to
Hmm.
limit it to just like ImageNet image, right? You can maybe have some like creative composition that's synthetic, does not exist in the real world, right? But
Hmm.
somehow
So
this
you're
feature,
saying,
yeah.
if I understand correctly, you're saying the source of well, here it says real image, but the source of the image, the
Mm.
synthetic image in this case, would be itself the output of the generative model, and then you would still use the generative model for feature extraction, and you would
Mm.
then feed that through the backbone.
Yeah, that's right.
Okay.
That's right. I think the good way is like um, let's say you have like internet scale pre-training images, right? There's a lot of image, but um, because your generative model has seen those image a lot, right? You can like get this like new. Let's say you have two example. For example, um, how to say that um, because the generative model is learning a distribution, right? You will learn
Hmm.
to extrapolate or interpolate between examples, and you want to see as many images as possible for your pre-training. But usually, you see in the real world scenario, you cannot exhaust all the possibility, right? But using synthetic data, because your generative model has some ability to, imagine some example in between, you can basically just think about it as like a data augmentation, right? Because you can augment infinite, training data,
Hmm.
that will make your pre-training more robust to any new unseen scenario, right?
Hmm.
That's the advantage of synthetic um, pairs.
I get the point. I also see risks with using synthetic images,
Mm.
like particularly if you're Um, like I think a lot of synthetic images have maybe they have a particular style associated with them often, kind of like less photorealistic maybe and more dreamlike in the style, at least from
Mm.
the image generators that I've seen. Is there a risk in using synthetic data that the
Mm.
features that you're training on are not as good as if you would use real images?
Yeah, it's maybe it's a little bit beyond this topic, but my perspective is like you can think about it as you can think about a generator as like a data set mixer. is trying to, so for example, when you do pre-training on only the real image, right? It's very hard to control the distribution of your data set. Let's say you just only collect randomly from the internet. How can you ensure, for example, the fairness or the, some scenarios are seen more often or less often, right? It's very hard to control. So your pre-training becomes like, one thing is less controllable. Second is like not robust for some what we call like long tail distribution. Let's say you never see some scenario like I don't know, some rare situation happens in the street or something like that. But you can fix that or you can mitigate that by, this generator, because you can control, let's say, oh, I want to, synthesize more on this rare scenario because by definition, this generator, you can always filter that, right? Like you said, you can see some like maybe less realistic samples, but you can always control that by some filters or by some like rejection sampling techniques, right? Yeah, in that sense, and also it's also good for the pre-training, because usually pre-training is like you want to see more concepts, but under like very different condition. It can be, for example, like the same object. It's under different filters, right? Like different lighting situation, which is rarely see. For example, if you see like someone is in an animation scenario, someone is in some street, like super realistic. So in that sense, like synthetic data will make the image backbone much more robust, because it sees the same concepts under different scenarios because of the synthetic data.
Understood.
Yeah.
So, given that we have the picture on screen here now as well, I think we covered to a large extent what happens up until this regression loss here. So, let's say that we train the image backbone so that the latent space is now more or less aligned with the features that we were aiming to align it with. How do we then take the image backbone and transform that into something that actually extracts features that we're looking for? So it seems to me like there's a step that goes beyond this particular training, and maybe it's outside the scope of the paper, but just for my reference, it would be useful to know what steps do we take after we align these intermediate features.
Yeah, so I think I did not mention this also, like label distillation here in the paradigm. So maybe I just quickly mention that. So before the feature regression loss, right, on the left side. So it's all about like pre-training on unlabeled data sets, right? You don't need any label, just like image. But let's say maybe for some tasks you have some small set of labels, which is super common for self-driving or for robotics, right? You have some small demonstration. You have a lot of unlabeled videos, but you only have a few supervised labels, right? So what you can do is like you can jointly train this with what we call label distillation, because you have a generator, right? So the same features here from the generator, you can pass it in what we call like feature interpreter, right? So basically, it's like it taking the generator features and it trying to output some labels. In this case, it's like semantic segmentation, right? So it's basically a mapping from the generator's feature to some label space. So because it's a generator, you can now synthesize infinite. So with a little bit of supervision, right? You let's say you train this feature interpreter, and then you can always like sample new samples, right? You can always sample some new image, and you can get the synthetic label for free, right? Because it's a generator model. And although the accuracy, right, the accuracy of the label might not be as good as like human label, but in what we found is like it's super robust with a little bit, maybe like 1%, 2% of the labels, you can get like very good accuracy for the data quality. So basically, what you can do is like you can jointly think about this label distillation as like one of the pre-training steps. You're jointly training with the features plus these synthetic labels, right? So if you want to solve just one task, right? But if you just like want to have like general purpose pre-training, so after the pre-training, you just drop all the things. You just only use the image backbone, right? You do some supervised fine tuning. That's also fine, right? You don't need to worry about the rest of the part because it's like a general backbone. You can just fine tune on the downstream task. It's also one way to use it.
Okay, understood. So then, with the last few minutes that we have, I would like you to quickly just mention the results. We're not going to have time to give it proper justice with a few minutes left, but if you want to just summarize what you found as far as results go, and then we will put the paper in the description so that anyone interested can look at more details.
Yeah, sure. So yeah, I think for the visual like qualitative results, you can see for uh, appendix, right? For example, for uh, figure 9, figure 10, you can see uh, if you only use, for example, like a very few amount of labels.
Okay, these are the ones.
Yeah, so usually those like par labels are super hard to collect, right? So we demonstrate here like with only, I think very few, maybe less than 50 labels. You can do semantic segmentation on the detailed parts of the human faces. We have more for other scenario, like for example, Alsan, bedroom. Um, if you go down a little bit, yeah. So I think with only a few labels here, like under 50 or something, for the demonstration, you can basically um, do segmentation super well on the downstream task using the image backbone we pre-train. Yeah, that's qualitative. But if you go to table 1 and 2, yeah, so here is like some numerical results. As I said, you can see some like common like popular method like Dino, MAE, or Sparks K that after pre-training, if you do some supervised fine tuning for image class, so usually we found with this pre-training like feature distillation, usually the backbone is much better at like dense prediction tasks like semantic segmentation or detection tasks. You can see here for detection or segmentation, image, sorry, the number improve a lot, right? Like by 1, 2 points under a fair setup. But usually it's like a little bit worse than classification. I think the hypothesis is like basically because we do this feature alignment for the generators, so those features are maybe more fine grained, other than like more abstract, right? So it's more suitable for if we want to do, for example, like detection, segmentation, depth prediction. Maybe it's more like suitable for this kind of pre-training. Yeah.
Why do you think those features might be more low level from the generative model?
Yeah, because the the generator is trained to, um, generate pixels, right? So if you want to generate the pixels well, you need to understand the semantics. Usually the semantics are more like fine grain parts, details, high frequencies, right?
Mhm.
So, but like for image classification, usually you need to know more about like abstract, very coarse, like global features to distinguish between different classes. Other than those like little details, for example, like whether it has wrinkle or not on your faces, those are like super fine grained details. You might not need to know for classification, I think.
Yeah.
Yeah.
Okay. Very good. We should wrap it up. I don't know if there, so as a last question, if there are any things that you think would be useful to take this
Mm.
study further. Was there anything you didn't have time to do that you would like to do? Yeah.
Yeah. So I think at that time we trying to constrain the experiment to only ImageNet, right? But
Mm.
we I think it would be super cool to scale it up to, for example, Lion or some in the wild image, not just limited to ImageNet setup. Uh, that's one thing. I think another thing is about, um, whether we can, put more effort to unify this um, backbone and the generative models, right? So as
Mm.
you can see here, like for example, like VIT or ConvNext, right now they are designed to be super good at discriminative tasks, but for diffusion model or for um, other type of generative model, they also have like some design choices just for the generative model. So whether we can
Mm.
unify these two models so that we can just show, okay, we don't need to distill features, we can just pre-train that and then use the same backbone for the task. That will be ideal, I think, uh, in the future scenario. Yeah.
Mm. Perfect. Then let's wrap it up there. I appreciate you taking the time to go over the paper. I enjoyed the discussion, so thank you very much for doing that. And yeah, that's it.
Okay, thank you, Nicholas.